Good day to everyone. It's a pleasure to welcome you all in this LE webcast today, speaking about the topic of power system flexibility in the quite far future, looking at a 2050 time frame in which the European power system could be covered by 100% renewable electricity. The reason for talking about this issue and diving a bit deeper into this is, of course, to look a bit forward and see what the recent Paris Agreement of 2015 on decarbonization actually would have as an impact and would require in terms of solutions to reach these objectives, of course. Translating the COP21 agreements would result roughly in zero carbon emissions before 2050, even about a 50% reduction in total energy demand by 2050. And a full decarbonization of the electricity system actually before 2050 still, to make sure we meet the 2%, the 2 degree or even 1.5 degree scenarios as committed to. When we look towards a decarbonized power system in Europe by the time frame of 2050, some of the main components have been well discussed and understood in recent years already. A decarbonized system will require a dominant renewable in-feed on the supply side. This change in energy will also require a much higher need of flexibility, which is higher and different compared to that of past decades. Basically, we all start to understand that flexibility can be offered via supply, also via demand, also via storage. And to make all of this function, we would require a strong, appropriate grid infrastructure and adequate markets, of course. But so far, there hasn't really been a fully detailed study available which looks to the optimal combination of all flexibility deployments in a full renewable system in Europe by 2050. How all of that would work, how much generation flexibility, demand flexibility, storage flexibility would you need to ensure all your fundamental demand can still be met, of course. There is a good share of interesting studies conducted in the past years, of course. They all have their own angle, their own scenarios, their own optimization focus. And what we try to do in this small exercise we're presenting here today is to a bit take a close overlook of those available studies, connect the dots, and try a bit to understand where all these flexibility options are heading towards for 2050. To put it in a different context, you could say in Europe we're progressing in stages of RES deployments towards what 2050 could be like, 100% decarbonized system, predominantly supplied by renewable sources. Initially, when renewables started to come online in the system, it was, well, learning by doing, fit and forget, not really fundamental changes. When we reached a few percentage of renewables, new market players started popping up, policy started to adapt, and in Europe we started to go forward with the means of targets to reach even higher penetrations of renewables. I think you could say today we are in the full transition mode. There are fundamental changes in how the market works, how the responsibilities of all parties are being scheduled, of course, and we all understand a huge effort is needed to go to even higher shares of penetration. And all of that cross-sectoral and cross-country collaboration is, of course, key. And we look forward towards the last stretches of going towards 80, 90, perhaps 100% renewable in feed by 2050 or even earlier in Europe. And what is actually needed to make those last stretches of renewable increase happen? Various studies, they try to look in that dimension, and it's quite interesting to see what they analyzed and what they came up with actually. To make it a bit more tangible, what could be the challenges in a really 100% renewable-based system in Europe in 2050? I show this graph, which is a graph people often use to show the impact of larger shares of renewable in feed. It's what we would call a residual load curve. If you would look at all 80,760 hours on the year, look at the electrical consumption, and you would sort it all, you would get something like the blue line on top, a load curve. If you would deduct from that load curve the variable renewable in feed, like solar, hydro, wind, you would get what is called a residual load curve, meaning the load which still has to be supplied via dispatchable generation, via storage, and perhaps where also demand response can have an impact. With higher shares of renewables, your residual load curve will go lower, but it will never become fully flat. You will go towards something like the black line and even lower. You would have situations like shown on the right-hand side where sometimes in the year you have an excess of renewable in feed, and you would have situations like on the left side where you would still have residual load which cannot be covered by renewable in feed at that point in time. And how do you make sure residual load can always be supplied? You can push for energy efficiency, of course, or you can look for means of flexibility, as said, in storage and demand response and pooling of resources across borders. And that's the challenge we really are facing if you look towards a 100% renewable system by 2050. Which levels of flexibility are needed to make sure residual load can always be supplied? In this graph, it's just a very rough shot at how a residual load curve in 2050 could look like. We picked an available renewable scenario from one of the main European studies. We checked a bit what people understand today are already interesting options of demand flexibility. You see the list on the left side. And we tried to do an analysis if you would apply all these demand flexibility options. You would be able to shift demand with a few hours. How would your residual load curve be impacted? And even if you would push for 6 hours demand flexibility, or even 24-hour demand flexibility, there is some impact in the annual peak load which is being reduced, or the situation of excess renewable in feed also being a bit mitigated on the right-hand side. But overall, the impact is not that huge. So we're still missing a few necessary options to make sure we can operate such a 2050 100% renewable system. So what more is needed in terms of demand flexibility or in storage options? Let's take a closer look at what some European studies have said on that topic. Before diving into that, I just want to sketch a few fundamental questions which of course exist if people talk about a 100% renewable power system. It's always a question about which are the shares of renewable technologies in that system. How many percentage of truly variable renewables would you have, like solar and wind? How much renewable would be fully controllable, like biofuels, and how many would be highly controllable, like hydro, for example? Fundamental question would be, do you still need X% of dispatchable generation as backup to make sure everything can still function? Would you need more biofuels, or would you still need to have some other gas plants as backup capacity? How do you cope with fluctuations not only at a day level, but also at a seasonal level, if you would assume high shares of solar, for example? And if you look forward, how do policy and planning strive actually for an optimal design of all of this? Today, if renewables come online, it's normally with priority access. They can feed into the system. But if you would go for very high shares of renewables, you would meet some points in time, as shown in the residual load curve, where there would be more renewable in feed than actually demand is at that point in time. So if there is not sufficient demand flexibility and storage, would you be okay with a situation where rest would be curtailed? Would it become common practice in that kind of system? And to which extent can you really make use of demand flexibility and all of that? A lot of questions pop up, of course, if you start talking about a 100% renewable system. And it's interesting to always look at how available studies have already tried to give an answer to these kind of questions. In our analysis of looking at a few available recent 2050 European power system studies, I would say the ones you see listed here are the main reference ones of the last years. There are quite extensive studies already available for us to read, understand, and learn from it. Firstly, I would refer to the Electricity Highway 2050 study, which is a study which looked at pan-European transmission grid needs in 2050 for various scenarios, one of them also being a 100% renewable scenario. The second one is the Energy Storage Mapping Project for the European Commission, which looked at the potential of large-scale storage also by 2050, how much really geological potential is there in 2050 for large-scale storage, and how could you make use of that. The third one, also quite often referenced in various documents, it's the Fraunhofer Optimal Pathway Studies, which also looked at a cost-effective design of Europe in a 2-degree scenario. There is the European Commission's own reference scenario based on Prime's modeling, which actually is, you could call, a business-as-usual scenario. It looks at 2050. It covers quite detailed modeling of all energy vectors we have, but it undershoots the targets we all have in mind for 2050. But it's still interesting to see what a business-as-usual scenario would give, of course. And fifthly, I would mention the Greenpeace study, which did a global analysis of how a cost-effective energy system could look like, also with various scenarios, one of them also being what you could call a COP21 compliance scenario. We looked into all the studies. We tried to understand how they did their modeling, which kind of assumptions they made, which kind of issues they highlighted, but also how they saw various flexibility options being pushed forwards towards 2050. So a very rough figure you see here is actually the capacities those studies give in terms of supply, demand, storage, and grid for 2050. How much of those flexibility options would you have in the system? And let's take a closer look to all four of these elements in the next slides. To start with flexibility via the supply side in 2050, today Europe has about 1,000 gigawatt of installed generation capacity, and various studies point out that it will be something between a 50 or 120% increase in installed generation capacity by 2050. So a lot more generation, which of course is understandable since we're talking about replacement of fossil fuels by renewable installations, which have lower capacity factors. So that makes perfect sense, of course. And all these new generation plants, on their own, they will be flexible in terms of easily controllable. They can provide frequency regulations. That's not the issue, of course. The main fundamental question remains, are they able to supply when demand is asking for it, of course, since only part of it will be really dispatchable, of course. You can always curtail a bit of wind and solar, but you cannot really increase it, of course. So how much of the dispatchable generation would you still need in your system? Will energy curtailment really become a common practice in 2050? Most of the available studies are quite silent about that. So those are some interesting questions to still flesh out, of course. And then there is the ultimate technical question, of course. If you would take out all those large generation plants you see nowadays in Europe and replace them all via these new kind of installations, which are quite often inverter coupled, would that give some interesting technical challenges still we would have to overcome. Secondly, looking at demand flexibility, I would say the knowledge we have is a bit more gray compared to generation flexibility. If you look at the studies we just highlighted, demand flexibility ranges somewhere between 20 and 150 gigawatts in 2050. And it's most often based on a few very simple assumptions many parties use. For example, saying that of the peak load, about something around 10% is assumed to be controllable, and making an assumption on the increase of heat pumps and electric vehicles and translating that then to demand flexibility. And that is basically how most studies actually play with the potential of demand flexibility. There's a huge amount of studies already available today which highlight what is the value of demand flexibility if you would assume a single installation or look at today's situation. But looking at it from the other angle, how much demand flexibility would you really need in 2050, or what is your total potential in 2050? Those questions, they remain quite unknown territory in many of the studies we have actually seen. Third flexibility element, storage. It becomes even grayer compared to the demand flexibility. Most of the studies which try to assess, analyze a 2050 almost 100% renewable power system in Europe, they don't really optimize the level of storage in the system. They just make an assumption. We will have X gigawatts of pumped hydro storage, and this will be the rise of, for example, dispersed battery installations. But how much do you really need? What is the tipping point of where issues could arise or where more storage would become unprofitable? That is really not. We didn't find any study which really tried to find that set point. And fourth element, how much grid infrastructure would you need in 2050 to make all of this work? As mentioned, one of the studies which looks at the 2050 100% renewable situation for Europe is the Electricity Highways 2050 project. They really try to analyze how much bulk transmission corridors would you need in Europe in such a scenario. And they came up with a number of about 100,000 additional main transmission corridors would be needed to make sure flexibility can be pulled from all over Europe. You can combine hydro from the Nordics with demand in Central Europe. You can take offshore wind and also transport it to Central Europe. These are the bulk transmission corridors you would need to make all of this function. But on top of that, how much local transmission would you need? How much distribution investments would you need? There is no single study which gives that number for all of Europe, and many studies try to analyze that at a local perspective, and also they go in all possible directions. Some studies saying you will need more grid, some saying you will need less grid because you go for other smart solutions. So also there is quite a knowledge gap still which could be and should be bridged in the coming years. So, as a summary and as ideas for thought and next steps, I would say, luckily, we know which direction we're going towards 2050 and which are the long-term objectives we really need to make happen. And there are several very interesting studies which try to understand what such a 2050 decarbonized power system would actually need, require, how it would function. But they all look at particular aspects, and you could say they're actually still scratching the surface, because there are still quite some fundamental questions we still haven't fully answered of what a decarbonized power system would look like. How would the market operate if you would have a large share of zero marginal cost generation? Would you still need backup capacity, for example, based on biofuels or even fossil gas plants? Would you be okay with situations where renewables would be curtailed for a share of the year? If you look at all your flexibility options, how do they all relate to each other? Actually, they're all competitors for each other, and there must be something like an optimal mix of flexibility solutions. If you go for more interconnection, would you need less large-scale storage? If you would really enable more demand response, would you also need less of the other flexibility options? There's still a bit of knowledge to be gained there, actually. If you really look for 100% renewable scenarios, and you would really think from the perspective which I showed at the start of the residual load curve across the year, we really need to start looking also into the need of seasonal storage even. What is the potential there? How much would you really need to make sure that systems with large shares of wind and solar can feed into this demand at all points in time? And especially for the topic of demand response, it's often being mentioned as the easy element, the quick win to make the system smarter and more flexible. What is the real potential for demand in 2050? So I think our knowledge is starting to increase, but there's still some interesting challenges which we hope more studies will find an answer on in the following years. So with that being said, I hope it gave you some inspiration